Hello, I'm Dr. Abhishek Sharma. In this video, I will discuss pulse modulation and different types of pulse modulation techniques. So let us start. Pulse modulation. Pulse modulation is a type of modulation in which pulses are varied in some respect, such as the width or amplitude, to represent the amplitude of a signal. As I have discussed, there are basically two types of modulation. You can say the category of modulation will be either baseband or bandpass. Pulse modulation utilizes rectangular pulses and a periodic repetitive pattern of gate pulses, right? So pulse modulation is referred to as baseband modulation category and periodic pattern of rectangular pulses are used for this purpose, and we have to change the amplitude or the timing values, or you can say the pulse on and off time with respect to the messages. So if we are changing the amplitude of the pulses, then it will be considered as pulse amplitude modulation. This is your pulse amplitude modulation. When we change the width of the pulse with respect to the analog signal, this is our baseband message signal, you can say. This is a single tone message. So in this case, the pulse modulation will be considered as pulse width modulation. Other than this, there is another type of pulse modulation which is considered as PPM, that is called pulse position modulation. Pulse position modulation. Short form will be considered as PPM. So this is PPM, this is PWM, pulse width modulation, and this is PAM. This is pulse amplitude modulation. In these all three categories, there is one term which is common, that is a periodic rectangular gate pulses. So we can say that in pulse amplitude modulation, the amplitude of these pulses changes with respect to the message signal, or PWM will be considered as when the width of these pulses are changing with respect to the message signal. Similarly, PPM will be considered as pulse position modulation, where the position of the pulses is varying with respect to the message signal. This is the block diagram of pulse width modulator and pulse position modulation simultaneously. In this figure pictorial presentation, we can see that there is a block diagram where we are generating the modulating signal, or we can say that this is the section where you can apply your message or a signal, and then after that, this is a symbol of an op-amp, and you can see that this is considered as an open loop connection. So this is basically a comparator circuit where you are comparing your message signal with respect to a sawtooth generator. The sawtooth generation means like this. This waveform is considered as sawtooth. So sawtooth generator is generating the sawtooth wave, which is applying at the negative end of the op-amp. This is called inverting terminal of the op-amp, and at the positive terminal, non-inverting terminal, you are applying your message. So when you compare these two different waveforms, you will definitely have a pulse width modulation. I will explain this in for next slide, how you can consider and how can you draw the pulse width modulation. Similarly, when the output of this op-amp, that is a PWM, is applied to a monostable multivibrator. A monostable multivibrator means there should be a single output state at the output of this multivibrator, and you will get at the output PPM. This is called pulse position modulation. So monostable multivibrator's stable state will define, or you can say the duration of the stable state will define the position of the pulse at the output. So this is considered as PPM. This is a pictorial presentation of the waveforms at every mode. So you can see that this is a modulating signal. So in this line you can clearly see that this is a modulating signal, and this is a sawtooth signal. So at this end you are comparing your modulating signal with the sawtooth generator. So you can clearly see that at this point and this, from this time interval to this time interval, the sawtooth wave have low amplitude in comparison to the message signal. So as this is applied to the comparator circuit, so you can clearly see that as this voltage is low and our message signal is high in comparison to this sawtooth signal, so we will get the output as shown in the figure. So this is a positive output. As you know that comparator will always generate either VCC positive or minus VEE, depend upon the comparison. For example, if the comparison is positive, right? If at the non-inverting terminal, if the signal is high in comparison to this inverting terminal, then you will get positive VCC for the duration. And if VEE, or if you can say the inverting terminal, at the inverting terminal the voltage is higher in comparison of the non-inverting terminal, then you will definitely get minus VEE. This is reference to this figure, right? So at this point you can clearly see that as sawtooth wave is higher, so I am considering that, let us suppose that VE is equal to 0, then definitely from this duration to this point, you will get a 0 volt, as I have considered VE is equal to 0. Other than this, you can clearly see that from this terminal to this at this duration, you will definitely get high positive voltages, that is VCC, and so on. And from this duration to that point, this is again sawtooth signal is higher in comparison to the message, so you will get 0. Again at this point to this point, you will definitely see that in comparison of modulating signal, sawtooth signal is going lower in the negative voltages, so you will get a positive pulse, that is your VCC, right? So this is your VCC. So this is the pulse width modulation output obtained from the comparator circuit. So and now I am applying this PWM to a monostable multivibrator. So you will see that monostable multivibrator when senses a pulse, right, a discharge of the pulse, it will generate a pulse for a fixed time interval, right? You can see that every time it generates the pulses, it will always have this is unstable state, and that is the output will be will depend upon the charging and discharging of the discharging circuits that are the parts of monostable multivibrator. Similarly, you will see that when discharge, this is a charge, right, and this is the discharge state. So monostable, when sense the discharging of the voltage, it will again generate a signal with the same amount of right, you can say the same duration of the pulse which is generated previously. So in monostable multivibrator, there should be a single stable state, that is a 0. In this case, you can see that pulse start and touch, let us suppose, a voltage A, and after a short duration it will again decay towards the 0 volt. So this 0 is the stable state of this multivibrator. So you can clearly see that whenever the discharge is sensed by the monostable multivibrator, it will again generate a pulse. So you can clearly see that this is the pulse position modulation with respect to the modulating signal, right? So you can clearly see that how this circuit is generating both PWM and pulse position modulation. This is the demodulation circuit for both pulse width modulation as well as pulse position modulation. In this block diagram, you can see that amplitude limiter is required. So you are receiving your, you can see that input PWM, PPM signal. Amplitude limiter limits the amplitude values because in a channel you can you know that noise added to the signal. So as when noise added to the signal, its voltage will vary in terms of amplitude. So amplitude limiter just clip some voltage and the level of the amplitude will become smoother in comparison to the previously where noise was added to that signal. So amplitude limiter is so much important. So amplitude limiter, after that ramp generator, the output will goes to the ramp generator, and the same side reference pulse generator. This input is also given to the reference pulse generator where it generates some rectangular pulses, and after that the ramp generator's output and these reference pulse generator output is added, and it again go to the clipper, and after that you will get your flat top PAM. Yes, definitely you have obtained the flat top PAM. The demodulation of flat top PAM has been already discussed in the previous videos. So this is a flat top PAM, and after that when you demodulate the PAM, when you use the PAM demodulator, you will get definitely your message. So how this demodulator works, I will explain with the help of the waveform. So this is the pictorial presentation of the demodulator block diagram and its waveform. So you can clearly see that at this end, like this is your 1. At this end, this 1 is representing the node. At this end, you will receive a pulse width modulated signal with some amplitude distortions, right? That's why I'm saying in the previous slide that amplitude limiter limits these amplitude variation. Like for example, it will cut some amplitude and maintain the constancy of the amplitude for its working time duration, right? So for example, you will get at node 2, you will get the output which is generated at this. So amplitude limiter limits the output, the amplitude of the output. So it will again become a pure rectangular pulses. And after that, as I've said that these pulses are applied to a RAM generator as well as reference generator. So at node 3, the output of the RAM generator, let us suppose this is node 3. So output of the RAM generator what will happen? This is actually you can say an integrator. So when you pass this constant to that integrator, it will generate it, or integrator just does a simple thing. It integrates. Let us suppose you are applying 1 dt, then you will get t. Definitely you will get t. So that is the constant ramp, right, for the duration, where for the same duration where the constant line that is this section is existed in node 2, right? Similarly, a RAM generator will generate at this point. Again at this, you can clearly see that and compare with the pulse width modulated signal at node 2, right? So this is the waveform at the output of the RAM generator. Now at the same time, this signal at node 2 is also passes to the reference pulse generator. So at this point, reference pulse generator, this is the node 4. So reference pulse generator always start the pulse at the end of this. Like for example, if this pulse is just what will happen, the reference pulse generator senses the discharge of the pulse and it generates a pulse, like at the output, and at the end of the pulse it will generate a rectangular pulses again and again. So this is the output of the reference pulse generator, and at this end, let us suppose this is the 5th node. So at this end you will get the summation of the signal at node 3 and node 4. So these two signals, this one and this one, will add it. So it will become like this, right? You can clearly see that it will add it at this point. And after that, clipper circuit, at the output of clipper circuit, actually it will clip some amount of voltages, and the remaining extra voltages, comparative voltages, will transfer to the output. So you will clearly obtain a pulse amplitude modulation, especially as the top is flat, so it will be considered as flat top PAM. And after that, when you achieve the flat top PAM, you will again pass it through a PAM demodulator, which is nothing but a low pass filter plus an equalizer. Right, so you will get your message. This is your flat top PAM. So this section is your PAM demodulator, especially flat top. For example, if at the end of the clipper circuit, if something is happening, like for example, if the voltage is too short, then you can also apply an amplifier, right, at this end to boost the amplitude of these pulses. So after that, you can also pass that to the PAM demodulator. So you can also add an amplifier between these clipper and PAM demodulator. Otherwise, it is not necessary if the voltage is accordingly proper, right? If your clipper also have an amplifier, then it will not separately required. I have explained pulse modulation, and in this pulse modulation I have explained that the pulse train the properties of the pulse train is modified accordingly. So the pulse modulation, there are basically three types of modulation techniques: pulse amplitude modulation, pulse width modulation, and pulse position modulation. So when you change the width of the pulse according to the message, then it will become pulse width modulation. If you are changing the position of these pulses according to the message, then you will get PPM. And if you are changing the amplitude of this pulse train, then you will get pulse amplitude modulation. So in this video, thanks a lot.